After you read the problem very carefully, my advice to you is to take a highlighter or just a pencil and highlight or underline the claim that you're trying to test. So here we're trying to test the claim that the defective rate of the process has increased, and increased from what? Increased from 0.2% of the time. So the next thing that you want to do is make sure you understand that this is a claim about a proportion value, not a mean value. So I will write down at the top here that P, the population proportion, represents the percent of defects, okay? For, again, remind yourself that this is for the population, okay? All right, now I am going to take a look at what I highlighted and convert this into symbolic form. So I'm going to put this in quotations. I'm testing the claim that defect rate, so the percentage of defect, the defect rate, P, right, has increased. It's greater than 0.2%. But let's make sure that we convert our percent to a decimal. So let me rewrite this as P is greater than 0.002. Okay, now let's highlight the, let me use my highlighter here, not that, but this. So notice that the original claim, and I forgot, let's keep track that this is the original claim, okay, has the greater than symbol. So this means that when I do the hypothesis test, the first step, which is to write our hypotheses, right, involves the null and the alternative hypothesis. The original claim becomes the null hypothesis. So P greater than 0.002 is the alternative. And again, keep track that that's the original claim, so you know how to write the conclusion in the last step. And then the null hypothesis is always the claim that P is equal to 0.02. So the null hypothesis always contains equality. We assume that is true, and then we try to find evidence to either support the alternative or not. Okay. Second step here is to calculate our test statistic. I'm going to go straight to the calculator function to find the test statistic. You are also welcome to use a formula to calculate the test statistic. Real quickly here, I'll write down that formula. That's P hat minus P naught over the square root of P naught times 1 minus P naught all over N. Or if you go to your calculator, I'm going to use red here, and use the function 1 prop z test. You're going to use this function because you only have one sample. The sample that we're talking about is this random sample of 1,400 parts where 3 of them were defective. So that's one sample prop because we're talking about a population proportion, Z because we are on the normal distribution where our test statistic is a Z-score, and test because you're doing a hypothesis test. Okay. One prop Z test is going to ask you to put in some relevant information. First thing is your null hypothesis claim. So here that would be 0.002. Then you need to indicate what X and N are. X is the number of defects, 3. N is your sample size, 1,400. And then don't forget to choose the correct alternative hypothesis symbol. So take a look at your alternative hypothesis. Note that it has the greater than sign, so make sure you choose that symbol. When you do that, the calculator will give you your test statistics. So it will say that Z is equal to 0.117. So that is your test statistic for your sample proportion value. Now, the calculator will also give you your sample proportion value, which is X over N. So 3 divided by 1,400 gives us a sample proportion of, what is that number? 0.00214. So if we're looking at this on a sampling distribution, so I'm going to draw that real quickly on the left-hand side here. If I'm looking at a sampling distribution of sample proportions, this distribution says this. If the null hypothesis claim is true, then we expect that every time we take a random sample and check the number of defects, right, the percentage of defects should be 0.002. So that should occur at a high frequency. So that's at the center of my distribution. That's my P naught value, okay? And if it's not exactly 0.002, then maybe it's a little bit higher or a little bit lower, right, which also occurs at a relatively high frequency, but it should not be that far off. But if the null hypothesis claim is not true, then that means that when we gather sample data, our sample data is either going to be a lot greater than 0.02% or it's going to be a lot less than 0.02%. So it's going to either be on the left tail or the right tail of this sampling distribution. So because my alternative hypothesis contains the greater than symbol, this lets me know that I have a right tail test where all of my significance level in my critical region is going to be on the right tail. So that's area that I shaded in red is going to be an area of 0.05. And then if you use inverse norm on your calculator, you'll be able to find your critical value. So that critical value is the z-score that separates that critical region of 0.05 on the right, and that number is 1.64. So that is your critical value. Okay, take a look at our sample proportion. Our sample proportion was 0.00214, which is slightly bigger than the null hypothesis claim of 0.002, or it feels like it's just a little bit bigger, right? The test statistic confirms that it's bigger than 0.002, but not that much bigger, because notice that its z-score is not even one standard deviation above the mean. So on this distribution, I'm going to use green here, and I'm going to label where that test statistic is. So at the center, our z-score is 0. Notice that our test statistic for our p-hat value of 0.00214, right, is only, so I'm going to mark that right here, is only 0.117. Okay, so not even one standard deviation yet. All right, that z-score or that test statistic of 0.117, right, also defines the p-value that I'm shading in green. So visually here, I hope that you can see that the p-value, the area in green, is greater than our significance area or significance level, the area shaded in red. We can go back to our calculator function, that one prop z test, and confirm that p-value. So that is the third step in a hypothesis test, getting that p-value. One prop z test will also let us know that that p-value is 0.452. So in step 4, when we make a conclusion or make a decision about the null hypothesis claim, we can see here that our p-value is much greater than our significance level. So we can say, since our p-value is greater than our significance level, and then write that down, 0.452 is greater than 0.05. This means that we will fail to reject the null hypothesis. Okay, so even though 0.00214 is a little bit bigger than 0.002, it's not statistically significant, so not strong enough evidence for us to reject the claim that the defect rate is probably still 0.002. So then now I'm ready to write my conclusion. I'm also running out of space, so I'm going to squeeze it on the left here, right? So what does it mean to fail to reject the null hypothesis? Because our original claim is the alternative, our wording will be, there is not sufficient evidence, and then you can add in there, at the 0.05 level, there's not sufficient evidence at the 0.05 level, right, to support the claim, that the defect rate, okay, for all parts, again, you want to make sure that you're referencing the population, right, is or has increased from 0.2%, okay? And that makes a lot of sense because remember, we did not reject this. We failed to reject, did not reject the null hypothesis claim. So because we didn't reject that, we're basically saying it could still be true. Therefore, our evidence does not support the original claim that the percentage of defects has increased.